In this section, we discuss the physics of ferromagnetism, which is one of the simplest and most studied examples of a system that undergoes a phase transition. In a ferromagnet, the spins transition at a critical temperature from an ordered net magnetic moment state to a disordered state with no spontaneous moment. Above the critical temperature, the spins only have net order in a magnetic field due to a paramagnetic susceptibility. Ferromagnetism is a model system that originated the concepts used to understand phase transitions and domain structures that are applied to ferroelectricity and other phase transitions in materials science. We start with the example of a simple material made from atoms with magnetic moment from spin 1/2 electrons. Recall that the magnetic moment of such an atom is quantized so that it can only be in two states: spin parallel to an applied field with a magnitude of 1 Bohr magneton in the direction of the field, or antiparallel to the field. Thus, the magnetic energy can only be in two states, plus or minus mu b times the magnetic field B, where the magnetization aligned state has lower or negative energy, while the state anti-aligned has positive energy. From statistical mechanics, we know that, in thermal equilibrium, the probability that the electron will be in either state depends on the energy of that state according to the Boltzmann factor, e to the negative of that energy over kT. The fraction of states aligned with the field is then the exponential of plus mu b over kT over the sum of the plus and minus terms. The spin anti-aligned equation has a similar form where minus mu b is in the numerator, with both terms in the denominator. This gives equations consistent with our expectation of equal population when the magnetic field is small, or temperature is high, and that when the field increases or temperature decreases, the population of the lower energy state grows towards 1, while the higher energy state's population decreases towards 0. The net magnetization is the difference between the density of aligned and anti-aligned spins times the Bohr magneton. Substituting x for mu b over kT gives e to the x minus e to the minus x divided by the sum of the exponentials. You might recall this is the hyperbolic tangent of x. M is small near 0 when the magnetic field is small because the spins are randomly oriented and there is little net magnetization. This also happens when the temperature is high, where high is defined as kT being large compared to mu b. When mu b is large compared to kT, M becomes large and saturates to a value of n mu with a curve described by the hyperbolic tangent function. When x is small, hyperbolic tangent rises linearly with a slope of 1, meaning tan hx is approximately equal to x. This means that m is approximately n mu times x, which is mu b over kT. Recall that the magnetic susceptibility chi is used when m is proportional to magnetic field, as it is here in the linear regime. Chi is m divided by the applied field, which we can approximate as b. So then the magnetic susceptibility is the number density of atoms with magnetic moment times the value of their magnetic moment squared divided by kT. Notice that n and mu are material constants, so that the susceptibility appears as a constant divided by temperature, which is observed experimentally and known as Curie's law for paramagnetic materials. Often, experimentally, 1 over chi is plotted versus T to determine mu, the magnetic moment per atom. Ferromagnetism is due to the atomic moments interacting with their neighbors to align them. In quantum mechanics, this interaction is called the exchange interaction. To account for this interaction, we simply propose it produces an effective field, like an additional magnetic field caused by all the other spins. We call this extra field the molecular field and presume the magnitude of its ability to align a spin is proportional to the net magnetization of the spins around it, characterized by m itself, or lambda m, where lambda is the molecular field constant that describes the strength of the interatomic magnetic interaction. The total effective field felt by the atom is then the sum of the actual applied field H and the molecular field lambda m. So now if we include the molecular field in the Curie law by replacing the H in m equals chi H with the effective applied field, we get m equals chi times H plus lambda m. Then replace chi with C over T, we get an equation with m on both sides. Solving for m gives the top equation. Simplifying the fraction by multiplying by t gives the middle equation. And then solving for m over h again gives the apparent susceptibility, the magnetization divided by the true applied field, which is the Curie constant C divided by T minus C lambda. We call this the Curie temperature, and this equation is known as the Curie-Weiss law. To summarize, the Curie law describes well the magnetization of a paramagnet as a temperature-dependent susceptibility that increases as T approaches zero, like a Curie-Weiss law with Tc equals 0. The Curie-Weiss law is used to describe the behavior of ferromagnetic materials when they are in their paramagnetic regime at high temperature, above the Curie temperature. As the temperature is lowered to Tc, the susceptibility diverges because the magnetization becomes large even with a small magnetic field. The inverse susceptibility looks like a straight line with an intercept, the slope being the Curie constant and the t-intercept is the Curie temperature, whereas a paramagnetic material has a 1 over chi intercept at t equals 0, a ferromagnetic material will have a 1 over chi intercept at the ferromagnetic Curie temperature. An antiferromagnetic has a 1 over chi that is a straight line heading towards a t-intercept less than 0. This is because the interaction is such that the spins are trying to anti-align their neighbors, so that the Weiss molecular field parameter is negative. When the spins of an antiferromagnetic actually align, the susceptibility no longer follows the Curie-Weiss model and depends on the ordered structure. Below the Curie temperature of a ferromagnet, the susceptibility has diverged to infinity because it has a spontaneous magnetization, meaning no magnetic field is required for the material to have its spins aligned and a net magnetization. This magnetization can be described with the same molecular field and the hyperbolic tangent function. When T is less than Tc, the interactions described by the molecular field are strong enough to keep the spins aligned even when the applied field is 0. At very low temperatures, all the spins are aligned and the magnetization is saturated at n mu b. As the temperature is increased, the magnetization decreases due to the thermal fluctuations. Near the Curie or critical temperature Tc, the magnetization drops precipitously and the material undergoes a phase transition from a ferromagnetic state to a paramagnetic state. Other phase transitions in material science are discussed using very similar descriptions. In a ferroelectric, where molecules have a permanent electric instead of magnetic dipole moment, a similar description applies, such that the terms ferroelectric and paraelectric derive from analogy with ferromagnetism. All phase transitions can be described with an order parameter like the magnetization in a ferromagnet, using a mean field description. For example, the structural order of a solid to liquid or a martensite to austenite phase transition. At low temperatures, there is complete order. At higher temperatures, there is some loss of order due to thermal fluctuations. Eventually, there is a critical temperature where spontaneous order is lost. Above Tc, the fluctuations are susceptible to ordering with an external field where the susceptibility is temperature dependent.